In this video, we are going to have the solved problems from roots of polynomials, which include finding the degree of splitting fields of certain polynomials and finding the automorphisms of certain structures. That will include integers, rational numbers, real numbers, and ring of complex numbers. All of them, even though other than Z, the rest are fields. Only the ring structure that we need to have the automorphisms, and then the rational roots occur in pairs and complex roots occur in pairs with the help of mapping. That how are we going to establish? So all these are going to be established in this video. First one, find the degree of the splitting field of this polynomial over Q. Now we know that splitting field is nothing but the smallest field which contains all the roots of the given polynomial. So if we need to know the degree, first of all we should know what that splitting field is. So splitting field can be determined only if we solve the given polynomial, I mean that given equation. So we consider this equation x cube minus 2 equal to 0. Then the roots of that, we have x cube equal to 2. But we know that whenever x cube equals 1, we have 1 omega square to be the roots. The three cubic roots of 1 are 1 omega square, or omega stands for minus 1 plus I root 3 by 2. So naturally your this polynomial will have its roots as 2 power 1 by 3, 2 power 1 by 3 omega, 2 power 1 by 3 omega square. And it is seen obviously that you don't have 2 power 1 by 3 as well as omega in Q. So that means with Q we need to adjoin our omega as well as 2 power 1 by 3. First have we to adjoin 2 power 1 by 3 and then omega, or omega first and then this. The order does not matter. Whether you attach A first and then B, or B first and then A with the base field F, that doesn't matter, which we have seen already. F of A comma B is same as F of B comma A. So that order doesn't matter. So first we shall give importance to omega. So since omega satisfies this, which is an irreducible polynomial over Q, we have the degree of Q of omega over Q to be 2. Because the degree of this will be, when we draw this tray diagram, we have Q base field with that adjoined omega, because in Q you don't have omega and you don't have 2 power 1 by 3 in Q of omega, so you adjoin this, you have this tower. But in order to know the degree of this over this, what is the polynomial this omega satisfies? Remember, it should be an irreducible or minimal polynomial. So here in this case omega satisfies this, so the degree of this over this is 2. And similarly, if you consider this, x cube minus 2 is the polynomial satisfied by this 2 power 1 by 3. Whether you consider over Q or Q of omega, this is true. So degree being 3, we have the degree of this over this one to be 3. But we want to have the degree of this over Q. So this degree of this over this into degree of this over this. So that gives 3 into 2, that is 6. So that is what is written here. If you take E to be the splitting field, then that E is nothing but, in this case, omega 2 power 1 by 3, Q of omega 2 power 1 by 3. So E over Q is E over Q of omega into degree of E over Q of omega into degree of Q omega over Q. So 3 into 2, that gives you 6. Then find the degree of the splitting field of this. So just by looking at this, we cannot say what is this degree of the splitting field of this polynomial over the base field. So in this case, it is not at all irreducible. We can split that into two factors like this. So if you multiply these two, you'll get back this. So this is the factor. These two are the factors of this. Now if alpha is the root of this polynomial, I mean this one, then obviously minus alpha is the root of this. Why? If you replace x by minus alpha, you get this. But that is alpha square plus 1 plus alpha equal to 0. That is what we have. But this is equal to 0 is the one that we need to check. This is what we need to check. But already alpha square plus alpha plus 1 equal to 0 because of this assumption. So naturally this will be 0. So the conclusion is when you have alpha to be a root, minus alpha is also a root. So we have the root satisfying a polynomial of degree 2. So E over Q in this case is just 2, degree of E over Q. What is E? E is just adjoin alpha to Q, so that will give the splitting field. Next is find the splitting field of this polynomial x power 4 minus 2 over Q. You have to solve this. The fourth roots of unity are 1, minus 1, I, minus I. So 2 power 1 by 4, 2 power 1 by 4 I, minus 2 power 1 by 4, minus 2 power 1 by 4 I. These are the 4 roots of this fourth degree polynomial. So in this case, again, you don't have I in this, so adjoin. And then you don't have 2 power 1 by 4 in this, so adjoin. Again, order of adjoining these two roots does not matter. So this over this, like this you can have, or you can also have Q of 2 power 1 by 4. First adjoin that and then. So order is immaterial. Now 2 power 1 by 4 satisfies 2 power 1 by 4 satisfies this polynomial, namely x power 4 minus 2 equal to 0. This is irreducible polynomial over Q. That is over what? That's very important. That's very important. So this satisfies polynomial of degree 4. Which one? 2 power 1 by 4 over Q. So this is 4. And I satisfies x square plus 1 equal to 0 is the minimal polynomial or irreducible polynomial satisfied by I. So degree is 2. So this is of degree 2 and this is of degree 4. So you have 4 into 2. This is 4, this is 2 and this one is 4. So either you can say like this, or when you consider this, here x square plus 1, so degree is 2, and here x power 4 minus 2 degree 4. So that you have this over this degree of this over this to be 4, degree of this over this to be 2. So degree of this over this will be 4 into 2, that is 8. So degree of the splitting field in this case is 8. So next we have x power p minus 1. Generally, where p is a prime number, we have to prove that if E is assumed to be the splitting field of f of x, then degree of E over Q is p minus 1. You consider x power p minus 1, which we can write as this, x minus 1 into this. So f of x, when it is taken as 1 plus x plus and so on, x power p minus 1, we have this cross multiplying, you get this. Now you consider f of x plus 1. So that gives us x plus 1 raised to p minus 1 by x plus 1 minus 1. So that you have as x. And in the numerator, when we expand binomially, this is what we get. So taking this 1 and 1 will get cancelled. Here also 1 and 1 minus 1 will get cancelled, giving this. In all that, what we have in the numerator, take out x and cancelling x, this is what we have. Now by Eisenstein criterion, f of x plus 1 is irreducible. Eisenstein criterion, the statement is given in the first section, namely 5.1 itself. So if you consider the statement goes like this, when you have the polynomial to be like this, and so on, a1x plus an x bar n plus and so on, a1x plus a naught. If there is a prime number which divides a naught and p divides a1 and so on, P divides A suffix n minus 1, but P should not divide an, and P square should not divide A naught. So if we have these conditions to be true, then the given polynomial is irreducible by Eisenstein criterion. So here we have P to be a prime number. That's very important. And we know from number theory that PCR, whenever P is a prime number, is divisible by P. PCR is divisible by P. That's also established in one of the videos under number theory. If you want, you can check that. PCR is always divisible by P provided P is a prime number. So, by Eisenstein criterion, these conditions being true, we conclude that f of x plus 1 is irreducible. And again, we are using a result that whenever f of x plus 1 is irreducible, then f of x is also irreducible. So, we have based on that, we conclude that our f of x is irreducible. So, this is a borrowed result. F of x plus 1 is reducible. Irreducible means then f of x is irreducible. So using that, we conclude that f of x is irreducible, and the degree being p minus 1, we conclude that degree of e over q is p minus 1. So next, as a particular case, we have x power 7 minus 1 degree of the splitting field of this over q we need to find. So if you take E to be the splitting field, then by the above argument we have degree of E over Q. Degree of E over Q to be 7 minus 1, that is P is 7 here. So 6. So directly like one word answer you cannot answer. You'll have to establish this. If this question is asked, you have to establish this and then say that here the prime is 7. So you have the answer as 6. Next comes the automorphisms of Z, Q, R and C. Very nice problem. Finding the automorphism, that only helps in finding the automorphism of another structure. So collection of automorphisms, how many that we will have, or do we have more or just one, or what could be that? So that is what is explored in this problem number 6. Find the automorphisms of all this. First we'll start with the Z. We do not know what the automorphism is, so let us name that as sigma. Let sigma from Z to Z be an automorphism of Z means the set of integers. Here ring structure that we consider, so you have this. Automorphism means you have that to be sigma to be 1 to 1 on to an homomorphism, ring homomorphism. So you have and also that homomorphism takes identity element to identity element, and this being bijective also it should take 1 to 1. Now you consider sigma of n. We can have n as a positive integer. You consider n to be a positive integer. Then sigma of n, when we consider n stands for 1 plus 1 plus 1 n times. But sigma be a homomorphism, we can rewrite this in this way. But we know that sigma of 1 is 1. So 1 plus 1 plus 1 n times. So you have this. Next you consider negative integer, sigma of minus n. N is again positive integer. So you have this one, sigma being a homomorphism, you have this to be minus of sigma of n. So sigma of n being a positive integer, by this it should be n. So you have this. So we even when we consider the 0 also, we have said, see, when we consider integers we have 0, negative numbers, positive numbers. So for 0 it is given here, for positive we have here, for negative we have this. So sigma of x equals x for every x in Z. The mapping which satisfies taking any element to itself with the domain and codomain the same is nothing but the identity mapping. So you have the automorphism to be just the identity mapping. There is only one automorphism from Z to itself. Now, in the same way, now we'll consider our rational numbers. Again, we do not know what that mapping is, so we shall take sigma to be that automorphism which we need to determine. Then when we have q means you have all integers, positive, negative, even 0, and q means you have other than that p by q, when p and q are integers with q non-zero. Now p being an integer, you have p is equal to sigma of p, because sigma is an automorphism. As far integers are concerned, sigma is only identity. So you can write integer as the image of sigma under the image of p under sigma. But this is rewritten as q into p by q. That is rewritten as q into p by q. Q into p by q. But q times p by q. So you have like this. Sigma is a homomorphism, so you can write like this. So how many times that you have? Q times. So we have q, this to be q into sigma of p by q. Q times sigma of p by q. So on the left side you have p, so p by q gives you sigma of p by q. So rationals are taken to rationals. So again, identity mapping only does this. So here again, sigma is just identity mapping. In integers, we had just identity, and here also. Next, we have real numbers. Let x belonging to R be such that x positive. Then sigma of x you can write as sigma of root x the whole square. Sigma automorphism. Again, as before, this is what we need to determine. We shall take it as some sigma. Sigma of root x into sigma of root x, but that is sigma of root x the whole square. That is also positive. Now, thus sigma of x is positive whenever x is positive. So we have sigma of a to be greater than sigma of b whenever a is greater than b for a, b, and r. Now, for any real number x, choose your a and b in q such that a less than x less than b. So your x is real number. Between any two rationals, there lies a real number. That's a result from real analysis. So we make use of that, so that that one will give us sigma of a less than sigma of x less than sigma of b. But we have sigma of a to be a and sigma of b to be, because for rationals just now we proved it will be only identity mapping. So you have this. So this gives, see here, a less than x less than b, and here we have this. So we, from that we conclude that sigma of x equals x. So identity is the only automorphism on R also. Now we go to complex numbers. Sigma from C to C be an automorphism. Then it should take a plus ib to some element over here. We want to determine what is, I mean, do we have sigma to be just identity or something else also? So you consider sigma of this is to be determined. So you consider sigma of a plus ib, sigma homomorphisms, you have this step. So a plus sigma of I into b and sigma of a minus ib. In the same way, when you consider, you have this. So sigma of a square plus b square, you know, you can write a square plus b square. See, what is that we have? Sigma of a plus ib is a plus sigma of I into b. And another thing, a minus ib we have as a minus sigma of ib. So sigma of a plus ib into sigma of a minus ib, that gives us a square minus sigma of I the whole square into b square, that into b square. So we have sigma of I the whole square into b square. But what is on the left side? It is sigma of a square plus b square. So sigma of a square plus b square is a square minus sigma of I the whole square b square. Now a square plus b square equals a square minus sigma of I the whole square b square, means you should have your sigma of I the whole square to be minus 1. So that in turn gives sigma of I to be either plus I or minus I. Now, why we get this one as this? Now, this is going to be a real number. By the previous subdivision, this has to be retained because sigma is the only automorphism on R. This is a member of R. So, you have this to be just this. So, by comparing, you can cancel out this a square, b is non-zero, so you can cancel out this. So, sigma of I the whole square is just minus 1, and a root of minus 1 you have plus or minus I. So which means there are two automorphisms. So one is it will take a plus ib to a plus ib itself. The other one is, for convenience sake, we can denote it as sigma suffix c. Sigma I identity, sigma suffix c conjugate. It will take to conjugate. So there are two automorphism. One is identity automorphism. The other one we can call it as conjugate automorphism, just for convenience sake, which takes any complex number to its conjugate. Now, having proved for Q, identity is the only automorphism, for this structure, do we have that to be anything else? So that is what is to be determined here. Show that the only automorphism, we are going to show it as just identity automorphism. So you consider phi to be a mapping from Q of cube root of 2 to this to be the required automorphism. Now, for all x in Q, we know that sigma can only, that phi could only be identity. So that is written, phi of x equals x. So yeah, x being in, 2 being an integer, you have phi of 2 to be equal to 2. But this can be rewritten in this way. Phi of cube root of 2 power 3 is also 2. So you have even root 2 the whole square is 2, but for the depending on the context that we consider, so you have this equal to 2. So what is your phi of cube root of 2? It is, you are taking cube root on both sides, so you have this. You do have omega square also, but your codomain is restricted to this. You don't, this does not admit your omega square, so that cannot be considered here. So you have only this. So as for cube root of 2 is concerned, it is also taken to this. Now you consider cube root of 2 square. So it will be, this phi is a homomorphism, so that can be taken inside. So you have this. So cube root of 2, this is taken to itself. Just now we had. So cube root of 2 the whole square. Again it is identity. It behaves like a identity mapping. Now you consider phi of a plus b cube root of 2 plus c into cube root of 2 the whole square. It is because phi is a homomorphism, you have this step, phi of c into this. So this is a, b quotient, real numbers, so you have b as such. Again this is proved just now, so you have this. Again this is also proved, so you have this. So you don't have a different element on the right side. Whatever you have considered, you have got back. So that means phi could only be identity automorphism. Now, to prove that real numbers are taken, the irrational numbers occur in pairs and complex roots occur in pairs, we establish one result and then go to those two problems. If E is an extension of F and if f of x is a polynomial over F and phi is an automorphism of E, leaving every element of F fixed, prove that phi must take a root of f of x lying in E to a root of f of x to another root of f of x in E. Now let phi from E to E be 1 to 1 on to homomorphism such that phi of alpha equals alpha for every alpha in F. If E, you first understand the question. If E is an extension f of x is a polynomial over f. Phi is an automorphism of E, leaving every element of f fixed. So it leaves the element of f fixed. That is why we have this step. And we are given this to be one automorphism means one to one onto homomorphism. So these are given to us. That is what we have written. Now what we need to prove is if a is a root of this, or say in this case we have considered delta. If delta is a root of this polynomial, f of delta, which means f of delta is a root. Now what we need to prove is phi of delta is also a root of the same polynomial. The image is also a root of the given polynomial. Under phi, where phi is an automorphism. That is what we are trying to establish. F of x, fx is a collection of all polynomials. N is an integer. All polynomials you have in fx. It is not restricted to just n alone. N is any positive integer. In fact, non-negative integer. N is any non-negative integer. Now you consider delta in E to be a root of f of x equal to 0. Then f of delta is 0, which means you can replace and that polynomial you take it as, say, nth degree polynomial, some degree we need to have, we shall take that as, say, an x power n plus and so on, a1x plus a0. So that your f of delta equal to 0 would imply this. Now you are applying phi on both sides. So phi being a homomorphism takes a 0 to 0. So you have identity to identity. So you have an so we have phi of delta. Phi of delta, that is we are taking so phi of a and delta power n, we are applying phi on both sides. So you have this phi of delta, you take it as some beta. So beta is a root of f of x. Beta is also a root of f of x. That is what we wanted to establish, and that we have got. And now we are going to prove that if delta is a complex root, delta conjugate is also a root of a polynomial in over Q. So define phi from C to C by phi of Z is equal to Z conjugate. See, we have already said that from C to itself we have two automorphisms. One is the identity and the other one is conjugate. So you have, we consider here conjugate automorphism, phi of Z equal to Z conjugate. This is known to as, it is one to one onto homomorphism. Now whenever delta is a root, just now we said that phi of delta is also a root of whatever polynomial that you consider. But according to this, phi of delta is delta conjugate. Therefore, whenever delta is a root, delta conjugate is also a root of this polynomial. So complex roots always occur in pairs. And then the next one is a plus b root m is a root of p of x. Then a minus b root m is also a root of this. So here you consider phi from k to k defined in this way. You put phi over here or here, that doesn't matter. Now you have you define the mapping in this way. Then phi is well defined. Here we are what is that k? K is collection of all. K is collection of all elements of the form a plus b root m, where a and b belongs to q. So you consider such a collection, and then in that whenever you consider a plus b root m to be a root of some polynomial, then for that polynomial this is also a root. Okay, so it is somewhat similar to the previous one. There you had the complex conjugate. Here you have for this the conjugate as a minus b root m. And remember, in this case we know well that this is one to one onto and homomorphism, but here we can easily establish that it is well defined one to one onto and homomorphism. So by the previous not previous problem, you have problem number 8. This one also to be a root. Which one? A minus b root m, which is somewhat similar to your conjugate. Okay, so a minus b root m is also a root. So irrational roots occur in pairs. So we will see the concepts of simple extension. Any finite extension is a simple extension. Very nice concept that we will see in the next video. Thank you.